Welcome to Let's Get to the Marks. I'm going through the GCSE Chemistry Higher Tier Paper 1 2019 for AQA. So let's get into this. All right, pause the video at the start of each question, have a go, then unpause the video and check out the walkthrough. Nice one. Let's go. Question 1 is about the periodic table. In the 19th century, some scientists tried to classify the elements by arranging them in the order of their atomic weights. Figure 1 shows the periodic table Mendeleev produced in 1869. His periodic table was more widely accepted than previous versions. Okay, so we got Mendeleev's periodic table here shown in figure 1. 1.1 says the atomic weight of tellurium is 128 and that of iodine is 127. Why did Mendeleev reverse the order of these elements? So obviously iodine was supposed to come first. Originally iodine came here in group 6 because it had an atomic weight of 127 and tellurium 128. Why did Mendeleev, and this is one of the funky things he did about the table, first of all he arranged like everybody else by atomic weight, but then he switched the order around and he put the heavier one before the lighter one. So they're basically asking you, why did he switch the order so they didn't fit by atomic weight? Of course, the answer is the properties of iodine fit with the other group 7 elements like bromine, chlorine, or fluorine. Basically, they had similar chemical properties. We could say tellurium had similar chemical properties to some of the other group 6 elements. So there we go. One of the genius things about Mendeleev, and one of the things you need to revise about Mendeleev, one of the 3 things is that he arranged it in atomic weight, he left gaps, and he also took account of chemical properties. Now 1.2 says Mendeleev left spaces or gaps marked with an asterisk. He left these spaces because he thought missing elements belong there. Why did Mendeleev's periodic table become more widely accepted than previous versions? So look, he left some spaces in his table. You can see them. They've got asterisks. I'm highlighting them here. Check out those asterisks. Now, elements should have gone there, but he was like, hey, I'm leaving a space here. Why later on did other scientists say, you know what, Mendeleev was right? And it's because the gaps that he left predicted the existence of new undiscovered elements. As those elements were discovered later on, after Mendeleev's time, they fit the gaps where he had made those predictions. And so they had similar chemical properties, these new elements they found, to the ones in the groups where the gaps were. So, and they had similar atomic weights. So it all fit and it provided evidence for people to go, do you know what? Mendeleev's table was good. So basically, we got a lot more evidence for it. Here are the ticks where you can pick up the marks. So, not memorize, but things to memorize about Mendeleev, about his periodic table. The most important things you need to memorize about Mendeleev's periodic table, put over here. So when you're revising Dmitry Mendeleev, however you say his name, you need to know that he arranged the periodic table just like the people before him by atomic weight. Now, they didn't call it atomic mass then, they called it atomic weight. But what he did do that was clever, he switched elements when he spotted that he switched them against their weight when he spotted the chemical properties would be more similar if he moved them into other groups. And this allowed him to leave gaps where later on they discovered elements to fit the gaps. So if you've got to remember 3 things about Mendeleev, he arranged a table by atomic weight, he moved elements into groups of similar chemical properties, and he left gaps. Let's move on. 1.3. Mendeleev arranged the elements in order of their atomic weight. What's the modern name for atomic weight? Well, I just mentioned that. We now arrange it by something called relative atomic mass, and that's the modern day way of saying atomic weight. So that's the answer to 1.3. Let's zing to 1.4. Complete the sentence. In the modern periodic table, the elements are arranged in order of... Well, actually, we don't arrange them in order of relative atomic mass. Let's check out a periodic table. How do we arrange them? Look, it goes 3, 4, 5, 6, 7, 8, 9 along the bottom there. What is that that's increasing? What's going up as we go across? What is going up? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. What is increasing as we go from left to right across the periodic table? Do you know what that bottom number is called? It's called the atomic number. So the modern day periodic table is actually arranged in order of atomic number, increasing atomic number from left to right across the period or across the rows of the periodic table. Now, if you're finding this walkthrough useful, don't forget to like, share, and subscribe. It really helps me, motivates me to make more past paper walkthroughs to help you get the top grades in your exams. Okay, let's move on to 1.5. So, chlorine, iodine, astatine are in group 7 of the modern periodic table. Astatine is below iodine in group 7. Predict the formula of astatine, the state of astatine at room temperature. We'll check out group 7. We can just come down here. Look, the formula AT, we've got it. It's below iodine. So the formula of the astatine molecule, we don't really need to predict because you're given the periodic table in the exam. So we know F2 is fluorine, chlorine is Cl2, bromine is Br2, iodine is I2, astatine is At2. Remember, the halogens are diatomic, which means they come in twos like this. Okay, what's its state at room temperature? Well, if we look at fluorine, fluorine is a pale yellow gas. Chlorine is a pale green gas. What's happening to the colors? Bromine is a red brown liquid, and iodine is a dark grey solid. Some people say black, but it's more dark grey solid. So what colour do you think astatine? They're getting darker as we go down. We're going yellow, green, brown, grey, black. Astatine is going to be black. So you're just following the pattern. Now, sometimes they ask this about the state of matter. So it goes gas, gas, liquid, solid. Astatine is going to be a solid as well. So it's just using your knowledge of the group 7 elements to make predictions about elements in group 7 you haven't come across before. 1.6, final part of this 10-mark question. Sodium's in group 1 of the periodic table. Describe what you'd see when sodium reacts with chlorine. You have to know this reaction off by heart. And solid silver sodium, it's a metal. It's going to react with chlorine, which is a green gas, green yellow gas, and it's going to form sodium chloride, which is table salt, which is a white salt. A white solid. Actually, sometimes if there's enough energy in this reaction, it's going to vaporize and you're going to get a white smoke instead of a white solid. But we could say the green yellow gas or the green gas or the chlorine gas disappears or the color fades. We could say the silver metal disappears because you're not going to see the silver metal either. And we could say a white solid forms. And just a little clue for all of you revising chemistry, any group 1, 2 or 3 compounds are all white solids and colorless in solution. So if it was magnesium chloride, white, aluminium chloride, white, lithium chloride, white, any compound of group 1, 2 or 3 is always white. So it's good to know that for observation questions. All right, let's move on.
Keep moving on, keep moving on, keep moving on, keep moving on.
Question 2, pause the video, have a go. This question's about acids and alkalis, or which ion do all acids produce in aqueous solution? So every acid, like hydrogen chloride, if you dissolve it in water, it will be aqueous. It will dissociate into H plus ions and chloride ions. So what ion would we expect all acids to contain? We'll take this second acid. This is sulfuric acid, H2SO4. It would also be aqueous. It also dissociates into hydrogen ions and sulfate ions. So what's the common theme with acids? What do all acids release? It's the H plus ion, the hydrogen ion. So you should notice all acids, you've got nitric acid, has the formula HNO3, and that will break down into nitrate ions and hydrogen ions, but all acids release hydrogen ions, H plus. Right, 2.2, calcium hydroxide solution reacts with acid to form calcium chloride. Complete the word equation. So we've got calcium hydroxide plus something acid makes calcium chloride. Well, it's going to have to be hydrochloric acid. Now, hydrochloric acid always makes chloride salts. So if we have magnesium hydroxide plus hydrochloric acid, it would be magnesium chloride instead of calcium chloride made. So salt and water is what you get for that one. Right, we're looking at 2.3 here. A student investigates the volume of sodium hydroxide solution that reacts with 25 centimeter cubed of dilute sulfuric acid. Figure 2 shows the apparatus the student uses. Name the apparatus. Do you know what these long glass things with a little tap at the bottom are called? You use them for titrations, and they begin with a B. Do you know the name of this apparatus? Used in titrations, begin with a B, used so you can add chemicals dropwise, and the answer is it's a burette. Superbulous. Let's go down to 2.4. What is the reading on apparatus A? Now, what you have to zing in here, you can see there's a curved line. We call this the meniscus, where the line curves. And you want to take the reading at the bottom of the middle of the meniscus, the flattest part of the curve, which is going to be at the bottom, the middle bit of that. So you're going to read that bottom of that line, and where that touches, that is going to be the reading. So here, look, I'm drawing a curved line here. You want to take that flat bit there, and where the flat bit at the bottom touches, that is the meniscus. So this I'm going to read, oh God, that all went shaky there for a second. Right, this is going to read 27.12345, and it's one more after the 5, so it's 27.6 centimeter cube. We read that as you're reading it from top down. So 27.6. And that's your answer, and that's going to get you 1 mark. 2 decimal places, 27.60. Right, let's have a little look here at 2.5. The higher the concentration of the sample of dilute sulfuric acid, the greater the volume of sodium hydroxide needed to neutralize the acid. The student tested 2 samples of dilute sulfuric acid, P and Q. Describe how the student could use titrations to find which sample, P or Q, is more concentrated. You should pause the video now and have a go at this on some rough paper, then unpause and watch the walkthrough. Okay, let's go through. First, use a pipette, right, to transfer 25 centimeter cubed of dilute sulfuric acid, P, you could start with Q if you want, to the conical flask. So we're going to put the acid in the conical flask first. Using the pipette, that's the perfect way, it's the most accurate way to transfer a volume of a liquid in chemistry. You always use a pipette. So at the indicator, phenolphthalein. Now, you don't have to use phenolphthalein or phenolphthalein. You can use methyl orange, which is the other option. I'm going to use phenolphthalein. That's colorless in acid. So if you remember that, you're going to get a mark. So it's going to be colorless to start with. A few drops of phenolphthalein, I should say, rather than just add 20 centimeters. I should have put a few drops. Fill the burette now with sodium hydroxide solution. We're going to keep the same concentration of sodium hydroxide solution for both when we do the titration with P and Q and any repeats we do. Add the sodium hydroxide solution. We could say, now you might have heard of this before, we could say carry out a rough titration. This will give you a rough idea of the endpoint. So you might know, oh, it's 23 centimeters, 22. This is going to make it more accurate and speed up the time taken to get to the endpoint when you repeat. Now, you don't actually use the rough calculation in any of your calculations. So now you can repeat and after the rough titration and then add dropwise, drop by drop, as you get near to the end point. When the color changes from colorless to pink, swirl the flask and wait to see if it's permanent. If not, keep going. If it's permanent, stop and record the volume of sodium hydroxide you added. Now repeat the titration again until you get something called concordant results. So these are results which are very close to each other. You should also use a white tile. It makes seeing any color changes easier, so that's going to score marks as well. Now we want to find the mean volume of sodium hydroxide added. And now we're going to repeat the whole thing again with Q. Now, the one where we have to add more sodium hydroxide is going to be the acid of the higher concentration. So once we find the mean volume of P added and the mean volume of Q added, the one we added more of is going to be the one where the acid was at a higher concentration. Okay, let me just shift all of this, get this a little bit more into focus so you can see the rest of this question. So now repeat the titration again as above, but using Q, find a mean volume of sodium hydroxide added to neutralize acid Q. And then we need to compare the 2 volumes, which we just said for Q and P. The one we had to add more sodium hydroxide to is the stronger acid. So I'm just putting in some marks here to show there's lots of marks on this question, and there's more marks. You can check the mark schemes on the AQA website. There's more marks you could get as well, but this is going to get you 7 or 8, and you only need 6 to get the maximum marks on this question. Right, let's move on. Okay, we're up to question 3. So this question is about materials and their properties. Figure 3 shows a carbon nanotube. The structure and bonding in a carbon nanotube are similar to graphene. Carbon nanotubes are used in electronics because they conduct electricity. Explain why carbon nanotubes conduct electricity. Now, what's the answer for this? Pause the video. Have a go. Now, any material that can conduct electricity as a solid in chemistry has to contain delocalized electrons. So, if you're looking at metals, you're looking at graphite, graphene, and it tells us this is like graphene, those can conduct electricity because they contain delocalized electrons. And if you're going to conduct electricity as a solid in chemistry, you have to have delocalized electrons. And the second mark for this is the same if the question was about metals, the same if it was about graphite, the same as if it was about graphene. The second part is that those electrons are free to move through the structure and carry charge. You mustn't say current, you must say carry charge through the structure. Current is the rate, the speed of the flow of charge. So don't say current because you're not going to get marks for talking about the speed that the charge is flowing. So the 2 marks for whenever something solid conducts electricity is delocalized electrons can carry charge through the structure. Okay, let's move on. 3.2. Of course, figure 4 shows a badminton racket, highlighting the frame of the racket. Table 1 shows some properties of materials. The materials could be used to make badminton racket frames. We've got aluminium, carbon nanotube, wood. And we got one of these questions which is kind of easy. It says evaluate the use of materials to make the badminton racket frames, 4 marks. You just need to use the information given to you in the table. And you just need to make relevant points about each. So you've got to do a bit of a comparison. So like if you're evaluating it, you're going to say, okay, which one is the strongest? Okay. So why would that make it a better material for a racket? Which one is the lightest? Why would that make it a better material for a racket? So you're just really going through and comparing and selecting the correct data and putting it into your answer. And that's really the best way to answer this question. Okay, here we go. So aluminium has a density of 2.7. So it's the heaviest. No, and that's not so good. Um, it's stronger than wood and stiffer, so less likely to bend or break, but it's weaker than the carbon nanotube. Wood is the lightest, so that's going to be a good thing because you're going to be able to like hold it for longer. It won't be as tiring on your muscles, so you can hold it for longer. However, it's also the weakest. Look at its relative strength. It's more likely to snap in a game. So again, that's not so good. Carbon nanotube, I would say, is has the best stiffness. You can see that it's got a 1000 stiffness, so that means it's less likely to break. And it's also the strongest, and it's light, so it makes it an excellent choice for making a tennis racket. Maybe the stiffness isn't so good; it won't be as flexible, but that would be my overall choice at the end. I'd go for the carbon nanotube because 2 out of the 3, definitely the strength and the lightness. It's medium light and it's the strongest, so pretty good. And the stiffest, so less likely to break. So they would be my reasons for picking the carbon nanotube. But you need to mention all of them, mention some numbers, and do some comparisons, and you should be able to get all 4 marks. Lovely jubbly. Right, we're smashing through this. Make sure you hit the like, people. It will help me out. Let's move on to the next question. So we're on 3.3. Zinc oxide can be produced as nanoparticles and as fine particles. A nanoparticle of zinc oxide is a cube with a side of 82 nanometers. Figure 5 represents a nanoparticle of zinc oxide. We've got 82 nanometer side. Calculate the surface area of the nanoparticle of zinc oxide. Give your answer in standard form. So hopefully you can work out the area of a cube. You're doing chemistry GCSE. So 82 times 82 will give you the area of one side. And then a cube has how many sides? 1, 2, 3, 4, 5, 6. Just about got that on there. So you want to do 82 times 82 and then times that by 6 and then make sure you put that into standard form. So what do they mean by that? You've got to use your scientific calculator if you want that in standard form, and then you just need to copy it out. So we got 40,344, but that's not going to be good enough. They want it in standard form. So we're going to convert that to 4 times 10 to the 4. And it does it say to round it? You can do 4.0344 times 10 to the 4. They should accept that as well as an unrounded version. And then you can round it to 4 times 10 to the 4. It doesn't stress that we need to do it to any significant figures. So you can have either one. All right, let's zing on. 3.4. Some sun creams contain zinc oxide as nanoparticles or as fine particles. Suggest one reason why it costs less to use nanoparticles rather than fine particles in sun cream. Nanoparticles are smaller, therefore they have a larger surface area to volume ratio, so you're going to cover a greater amount by using a smaller amount. So you can use less. A lot of people have makeup. A lot of the more expensive makeups like MAC makeup and stuff are made using nanoparticles now, and you only need a tiny bit on your finger and it can cover the whole of your face. And the same with the expensive sun creams, they're using nanoparticles. So you're actually using a smaller amount to cover a greater area. And it's because they are smaller particles, so have a larger surface area to volume ratio. Okay, question 4. This question is about atomic structure. 4.1. Atoms contain subatomic particles. Sub, like submarine, means below, so below the atom. So pause the video, have a go at this one, have a read through. Table 2 shows the properties of two subatomic particles. Complete table 2. So name of the particle is neutron, relative mass and relative charge. Well, a neutron has a mass of 1 and a relative charge of 0. Neutron neutral, it's not electrically charged. And then this is the proton. How do we know that? Because it says +1 electric charge, and protons and neutrons have the same mass. An element X has two isotopes. The isotopes have different mass numbers. Define the term mass number. So what makes up the mass number of an atom? Well, the mass number is the number of protons and number of neutrons in the nucleus of an atom. So the number of protons plus number of neutrons. And that gives us the relative atomic mass. Electrons have a negligible mass, so they don't really count as part of the mass number. 4.3. Why is the mass number different in two different isotopes? So what's different about two different isotopes? Well, they have different amount of neutrons, but all isotopes have the same number of protons. So they have the same number of protons, different number of neutrons. You can say it the other way around, different number of neutrons, same amount of protons. So it's the fact that two isotopes will have a different number of neutrons that will give them a different mass. Okay, the final part to this question is 4.4. The model of the atom has changed as new evidence was discovered. The plum pudding model suggested that an atom was a ball of positive charge with electrons embedded in it. Evidence from the alpha particle scattering experiment led to a change in the model of the atom from the plum pudding model. Explain how. So they expected most of the alpha particles to pass straight through if the atom was like a plum pudding. And they fired them at gold atoms, which are quite heavy and quite big. So tiny alpha particles should just pass straight through if the gold atoms were like a plum pudding. However, what they observed is that some of the alpha particles deflected and curved through, off on different paths. And some of the alpha particles bent straight back. They literally bounced and came directly straight back. The guy who did this, Rutherford, said it was like firing a cannonball at a piece of tissue paper and the cannonball bouncing back. That's how shocked he was. Most of the alpha particles did go straight through, and this taught them lots of things about the plum pudding model. The fact that 99% or 9,999 out of 10,000 went straight through told him that atoms are mostly empty space. But the fact that 1 in 10,000 bounced straight back told him that there was a very small, dense, hard thing inside the atom. And of course, that turned out to be the nucleus. And the fact that some curved through told them that the nucleus was positive. So they did learn that the nucleus is positive from this experiment. And they learned that it's small and dense. And they learned that most of the atoms are empty. And later on, someone else discovered, Niels Bohr proposed the different shells, the different quantum levels for the electrons. Okay, so this is just them showing they've got a source of radiation. They're firing the alpha particles at this curved sheet of gold atoms, and what they found is they thought that they would all go through. Some did go straight through. Some curved away because the nucleus is positive and alpha particles are positive. So some got repelled and curved away, and some of them bounced straight back, and that's because they had a direct hit on the nucleus, and that told them that the nucleus must be hard and dense in order to bounce an alpha particle back. So look, most have gone straight through. This is an atom rather than a gold sheet this time. Some have curved away from the nucleus because alpha particles are positive and the nucleus is obviously positive. And then some, which I've drawn with a green line here, had a massive deflection, and that's because they scored a direct hit on that positive nucleus. And so this gave all the evidence for the nucleus. No one had actually seen a nucleus, or still to this day probably has ever seen a nucleus, but we've got the evidence for it. So let's go to question 5. This question is about ammonia, NH3. Complete the dot and cross diagram for the ammonia molecule shown in figure 8. Show how the electrons in the outer shell show the electrons, I can't even speak properly, show only the electrons in the outer shell of each atom. Now you'll get a periodic table. Hydrogen might as well be group 1, it's only got 1 electron. Nitrogen's in group 5, so we only need to show the outer electrons. It's in group 5, it has 5 electrons. There's nitrogen's 5, it's going to share 1 with each hydrogen, and hydrogen itself only has 1 electron. It's going to share 1 with nitrogen as well, and they're all going to be nice and happy with full outer shells like that. Wonderbar. Okay, 5.2. Give one limitation of using a dot and cross diagram to represent an ammonia molecule. So what's the limitation of using dots and crosses? Well, it doesn't actually show the shape of the molecule. It actually doesn't show the length or the size of the bonds, and it's only two-dimensional, so we can't see the three-dimensional shape that the actual molecule has. It's actually shaped like a pyramid, just like this. I'm drawing it over here on the side in green. It's actually shaped like a pyramid, actually, this molecule. But yeah, so that's my crusty pyramid over there. That's how that molecule is actually shaped, but you wouldn't know that from the dot and cross diagram. So it's kind of, that's a limitation. 5.3, explain why ammonia has a low boiling point. Now, every time in chemistry, every single time, doesn't matter what they say, if they tell you something has a low boiling point, it has the same answer every time. If they tell you something has a low melting point, it has the same answer every time. So just memorize this answer. It comes up every year pretty much. Refer to structure and bonding. If you've got a low melting or boiling point, chances are you are a simple molecule. Also, any gas or liquid at room temperature is going to be a simple molecule. And if you're a simple molecule, you have weak intermolecular forces. If you can't remember that, you can say weak forces between the simple molecules. These forces are easy to break and do not require a lot of energy, hence the low melting and boiling point. So once again, every liquid and every gas at room temperature in the room with you now is a simple molecule. Every chemical with a low melting and boiling point in GCSE chemistry is a simple molecule. So the answer is simple molecule, weak intermolecular forces, easy to break. Smashing that exam if you can just memorize that. You can apply that in every single chemistry exam. Every time they say, why has this got low boiling point, melting point? Why is this a gas? Why is this a liquid? Boom. Right, moving on. 5.4. Enough of my lectures. Ammonia reacts with oxygen in the presence of a metal oxide catalyst to produce nitrogen and water. Which metal oxide is most likely to be a catalyst in this reaction? So there's a certain section of the periodic table which has the catalysts, and they're known as the transition metals, and they make good catalysts. Group 1, 2, and 3 metals do not make good catalysts, so we're looking at a transition metal. So calcium oxide, well, calcium's in group 2. Magnesium oxide, the third one down, magnesium's in group 2. Sodium oxide, the fourth one down, sodium's in group 1. So you're looking at that middle block in the periodic table, and you'll find chromium, I think that says Cr2O5 or something. That is a transition metal. So anything that's from that middle block, like iron or copper, nickel, they're all great catalysts because they're transition metals. They can have more than one oxidation state. They can form different charged ions, like iron can be 2+ or 3+. Right, figure 7 shows the displayed formula equation for the reaction. And we've got a reaction here. Calculate the overall energy change for the reaction. Use figure 7 and table 3. So let's zing in and calculate the overall energy change for this reaction. So for this bond energy calculation, we need to work out the bond energy on the left over here, which is the bond breaking. Then we need to change the arrow in the middle to a minus and then work out the total amount of energy in the bond making. And then we just set that out like an equation and work out the answer. So how many of these NH bonds are there? 391. There are 3 times 391. Now you're going to get marks, you're going to pick up marks for some of these. So we've got 3 times 391, but look at the big 4 in front, the coefficient. So you've got 4 times 3 times 391, or you could do 12 times 391, and that equals 492. Then we've got this oxygen bond, 498, and we can see there's a big 3 in front, so we've got to do 3 times 498. We're going to add these together. We'll write down the big numbers because often on the mark scheme, if you fluff the overall calculation, you'll get a mark for some of this. So if we add those together, we get 6186. We're then going to put minus. Now we work out the energy released in bond making. And we've got 2 of these NN or nitrogen bonds. So 2 times 945, which equals 1890. And then we've got 6 times OH, but there's 2 of them in each water molecule. So really, it's 12 times OH, or 6 times 2 times 464. So you've got to do 12 of those, and that equals 5568. We add that to the original 1890, and we'll get the overall energy released in bond making. And it's 7458. So we want to do 6186 minus 7458, and you're going to get a minus number, and that's correct because it means that more energy is released in bond making than when was absorbed in bond breaking. So this is an exothermic reaction, and the answer is minus 272 kilojoules. Okay, make sure you pause the video at the start of each of these, then have a go. So it's 5.6, explain whether the reaction between ammonia and oxygen is exothermic. Use values from your calculation you just did in 5.5, 2 marks. So the answer here is that the 7,458 kilojoules released in bond making is greater than the 6,186 kilojoules absorbed in bond breaking. So overall, 1,272 kilojoules are released. Is exothermic. (5.7) Figure 8 shows the reaction profile for the reaction between ammonia and oxygen. Complete figure 8 by labeling the activation energy, the overall energy change. So first of all, we have this like camel's hump here. This is always the activation energy, and you draw an arrow going up, and you can label it activation energy or capital AE or EA for energy of activation. And that's the energy you put in, the minimum energy required to break bonds. Now we have the arrow going down from this dotted line that we've made, and this is the overall energy change. And this one's exothermic because the arrow is going down. It's like a negative energy change. The energy is released. Right, we're on to question 6. This question is about chemical cells. A student investigated the voltage produced by different chemical cells. Figure 9 shows the apparatus. So we have a voltmeter, electrode X, a copper electrode, and electrolyte solution. This is the method used. Use a cobalt as an electrode X, record the cell voltage, repeat steps 1 and 2 using different metals as electrode X. Suggest 2 control variables used in this investigation. So the student is investigating the voltage created by different metals. We're going to want to keep the concentration of the electrolyte solution the same. You're going to want to keep the temperature the same. I'd probably say the mass of the electrode should be the same each time. So lots of different variables you can come up with there. And you only need 2 of these 3 to get both marks. All right, let's zing on. Table 4 shows the student's results. We have electrode X, it's got cobalt, copper, magnesium, nickel, silver and tin. We've got the voltage of the cell in volts for each one. 6.2. Write the metals used in electrode X in the order of reactivity. Most reactive to least reactive. Justify your order. Well, you're looking at which pair of metals has the biggest difference or which one has the biggest difference in voltage? So magnesium is plus 271. So that's going to be the most reactive. We've then got cobalt with plus 0.62 is the next most reactive. We're then looking at nickel, and nickel has plus 0.59. We're then going to go to tin with plus 0.48. Now, some people might make a mistake here, but copper is next with 0. And then finally, we've got silver with minus 0.46. And that's going to get you 4 lovely marks. Okay, let's move on.
Keep moving on, keep moving on, keep moving on, keep moving.
Now, part of this question said justify your order of reactivity. So here is the justification. The more positive the voltage, the more reactive the metal. Silver is the least reactive because it has a negative cell voltage with copper. Okay, coolio. Now let's zing down to the next bit of the question. 6.3. Which of the following pairs of metals would produce the greatest voltage when using the electrodes in the cell? So again, which of the two pairs of metals will have the greatest difference in the voltage? So would the greatest difference be between magnesium and cobalt, magnesium and tin, nickel and cobalt, or nickel and tin? Well, magnesium was 2.71, cobalt was 0.62. So you work out that difference. Then you've got magnesium was 2.71. And if we look in the table, we zing back up to the table and we say tin was plus 0.48. And then you say, is that a bigger difference? Well, that is a bigger difference than the 2.71 to 0.62. You can do all the others as well and look at those and see which one has the biggest difference in voltage. Right. 6.4. Hydrogen fuel cells can be used to power different forms of transport. Some diesel trains are being converted to run on hydrogen fuel cells. A newspaper article referred to the converted trains as the new steam trains. Suggest why. What is it that hydrogen fuel cells produce? So hydrogen fuel cells react hydrogen with oxygen and they produce water as the product. So water is released as kind of similar to steam, it's released as water vapor. And you've got this reaction, H2 plus O2 goes to H2O. Okay, question 7 is about electrolysis. Aluminium is produced by electrolyzing a molten mixture of aluminium oxide and cryolite. Explain why a mixture is used as the electrolyte instead of only using aluminium oxide. Well, we use a mixture, we add cryolite, and cryolite lowers the melting point of aluminium oxide, making it require less energy to melt, which is going to cost you less money. It's going to be more environmentally friendly. But the main thing here to get your marks are adding cryolite lowers the melting point of the aluminium oxide. And therefore, it requires less energy to melt the aluminium oxide. So 2 marks, cryolite lowers the melting point of aluminium oxide. Second mark, this means less energy is needed. Boom. Let's move on to the next question. 7.2. What happens at the negative electrode in the production of aluminium? So the negative electrode, the aluminium 3 plus ions, because aluminium oxide is made of Al3 plus and O2 minus ions, the Al3 plus ions have an opposite charge, so are attracted to the negative electrode. What happens to them? They pick up electrons. They're going to pick up 3 electrons because electrons are negative that will cancel out the aluminium 3 plus charge and form aluminium metal. So the correct answer is aluminium ions gain electrons. And we call that reduction. Reduction is gain of electrons. All right, let's check out 7.3. Oxygen is produced at the positive electrode. Complete the balanced half equation for the process at the positive electrode. So you can see what I've drawn here is a positive electrode, and the O2 minus ions, the oxygen ions, are going to go to the positive electrode, where they're going to lose their electrons and become oxygen gas. And each oxygen O2 minus is going to lose 2 electrons. Now, the problem is that oxygen molecules O2 require 2 O2 minus ions, 2 oxide ions, which means we're going to have a total of 4 negative electrons. Each negative electron, or each oxygen electron, has 2 E minuses on it. So look, we want to then make a covalently bonded oxygen molecule. Each oxygen is going to have to give away 2 electrons. So I'm going to need 2 oxide ions, each with 2 electrons in their outer shell, to come together to make an oxygen molecule and release those 4 electrons. Okay, explain why the positive electrode must be continually replaced. So the electrode, the positive one in the electrolysis of aluminium oxide, is made of carbon. You can say graphite, because graphite is an allotrope of carbon. And essentially, the problem here is oxygen gas is forming. Now, what do you think gets made when oxygen gas touches the carbon? Well, you get carbon plus oxygen is carbon dioxide. So carbon dioxide is formed at the positive electrode because it's made of carbons. We have a reaction between the carbon and the oxygen gas that's produced. And carbon dioxide is going to remove carbon atoms from the electrode. And that means it's going to erode. It's going to dissolve. It's not really dissolving. It's eroding as bits of the carbon are breaking off and becoming carbon dioxide gas. So you need to replace it because you're going to wear away that electrode. Carbon dioxide is a gas, but of course it contains the atoms of carbon that make up the electrode. So it wears away as the gas escapes. Super duper duper. Of course, the equation will probably get you 2 marks out the 3 for this. So always good to know. Let's check out 7.5. The overall equation for the electrolysis of aluminium oxide is, this is a 4 marker by the way, is 2Al2O3, 2 aluminium oxide molecules, form 4 aluminium atoms and 3 oxygen molecules. Calculate the mass of oxygen produced when 2,000 kilograms of aluminium oxide is completely electrolyzed. The relative atomic masses of oxygen are 16 and of aluminium are 27. Why don't you pause the video and have a go, and then I'll go through the answers. Okay, so the first thing you should notice is we've been given AR, so you need to know this equation, the most important one in chemistry, mass over MR times N. MR is the same as AR, you don't really need to worry about the differences between them. We've been given 2,000 kilograms of aluminium oxide, so that's the mass we've been given, and we've been given the AR. So everybody should be able to realize we've got mass and MR or AR. So I want to do mass over MR, and that's going to tell me how many moles of aluminium oxide I start with. So that's the first step. Now, if you mess this up, you'll still get them up, but you should really convert it into grams. And that way, instead of 2,000 kilograms, it's 2 million grams. You can still do it as kilograms if you prefer, but it's 2 million grams. We're going to divide that by the MR of aluminium oxide. So that's Al2O3. Do not times it by the coefficient, the big 2. You don't need to do that. So 2 times 25 plus 3 times 16, which is 48. So we want to do 2 million grams. Add those together. So we've got 54 plus 48. What's that? What's that? 102. So the mass of aluminium oxide is 2 million grams. The MR is 102. So we do mass over MR and we get 19,608 moles of the aluminium oxide. Now, in mole equations, once you've worked out the moles of the first thing, you've got to look at the coefficients. Now, for every 2 moles of aluminium oxide, we're going to make 3 moles of oxygen. So we need to convert this 19,608 moles, and we can times it by 3 over 2, or 1.5. And that's going to mean that we have 29,412 moles of oxygen. So you always use the ratio, those big numbers, the coefficients in a mole equation. So now I want to work out the mass of oxygen. I need to do the MR times the moles of oxygen. So 32, because there's 2 times 16 for the MR of oxygen, 32 times the moles, 29,412. I get 941,184 grams. If I want, I can, I need to, because the unit's kilograms, divide by 1,000. So I end up with 941.184 kilograms. And that is the mass of oxygen that will be released when 2,000 kilograms of aluminium oxide are completely electrolyzed. And there we go. Awesome. So, sodium, metal, and chlorine gas are produced by the electrolysis of molten sodium chloride. Explain why sodium chloride cannot be used as the electrolyte to produce sodium metal. Explain why sodium chloride solution cannot be used as the electrolyte to produce sodium metal. And this is one of the rules you need to know about electrolysis of solutions. Sodium is more reactive than hydrogen. And so if you electrolyze sodium chloride solution, you'll release hydrogen. The sodium metal ions will stay in the solution. They will not come off at the negative electrode. Hydrogen will be released instead. In fact, whenever you use a metal solution as your electrolyte, a metal compound solution, you're really only ever going to be able to extract copper. Calculate the volume of 150 kilograms of chlorine gas. Let's move on to the next question. Pressure. The volume of 1 mole of any gas at room temperature and pressure is 24. The relative MR of chlorine molecules is 71. So we know we have 150 kilograms. I want to change that to grams. And then I need to work out how many moles I've got and then times that by 24. So 150,000 over 71 is going to give me my moles of chlorine gas. Each mole of chlorine gas takes up 24 decimeters, which is 24 liters of space. So I need to work out that this is 2,112.67, and that's my moles. If I want, I could just leave it as 2,112.7 moles if I round it a bit. Now times that by 24, because each one of those moles takes up 24 liters or decimeters of space. So, and that's going to be our answer, 2,112.7 times 24. And the answer is 50,704 decimeters. Boom, that's a lot of space. Right, we're moving on to question 8. Copper from 2 oxides, copper oxide, copper 2 oxide, and copper 1 oxide. A teacher investigated an oxide of copper. You got tube A, tube B, a drying agent, excess hydrogen burnt off at the end, and we got heat under the oxide of copper. This is the method used. Weigh the empty tube A, add some of the oxide of copper to tube A, weigh tube A and the oxide of copper, weigh tube B and the drying agent, pass hydrogen through the apparatus and light the flame at the end, heat tube A for 2 minutes, reweigh tube A and contents, repeat steps 5 to 7, until the mass no longer changes, so you're heating till a constant mass. Reweigh tube B and the contents, repeat steps 1 to 9 with different masses of copper oxide. Wow, that's a big method. Right, pause the video, have a go guys at these questions, and then I'll go through the answers. All right, 8.1. So just one reason why step 8 is needed. So what we need to do is zoom in here on step 8, repeat steps 5 to 7 until the mass no longer changes. So why do we heat things in chemistry until the mass no longer changes? That tells us the reaction is complete and no more gas is being released, because as a gas is being released, the mass is going to decrease of something, or the mass will increase. Once a mass stops changing, it's a good idea that the reaction has stopped happening. So this makes sure all the water's been removed. You could get a mark for that, or all the copper oxide has finished reacting, and that will get you a mark. Let's look at 8.2. Explain why the excess of hydrogen must be burnt off. Okay, why do we need to get rid of hydrogen? Well, hydrogen's a gas, and it's not just a gas. You might know from the squeaky pop test, it's an explosive gas. So burning it off prevents it escaping into the air, where hydrogen's flammable and could gather somewhere in the room and cause an explosion. Yeah, pretty unlikely in a lab, but there we go. Right, let's move on to 8.3. So we've been given a set of data here, and we're going to get to do some calculations. The mass of the tube when empty is 105.72. Tube in the copper oxide is 115.47. Tube in the contents after 2 minutes, 11462. Then after heating till a constant weight, it's 114.38. So that's important. Tube B at the start is 120.93, and at the end 123.38. So we can tell here that tube A has been heated till a constant mass, because they heated it until they got two identical readings. We've got a drying agent here that is absorbing any water as well that is released. So the water is formed obviously when the hydrogen reacts with oxygen from the copper oxide. Determine the mass of copper and the mass of water produced in the experiment. First of all, to work out the mass of copper, we want to take the mass of the tube once it's been heated till a constant mass, so 114.38 grams. Now, that is once all of the oxygen has been removed and you're just left with the glass tube with copper in it. So it was copper oxide in the tube when it was 115.47, but once all of the oxygen's been removed, it's down to 114.38. So we've just got copper metal in the glass tube, so we need to minus the empty glass tube. So 114.38 minus 105.72 gives me the mass of copper, which is 8.66 grams of copper. Next, we need to work out the mass of water that's been released, and it's tube B that calculates this. So any hydrogen gas that comes through has joint with the oxygen from the copper oxide and enters tube B. It then gets sucked in and absorbed by like the drying agent. So the mass of tube B goes up. So to find out how much the mass of tube B went up, we do 123.38, which is the final mass of tube B, minus the initial mass of tube B, which is 120.93, and we find out that tube B went up by 2.45 grams. So that's the mass of water. So our mass of copper was 8.66 grams, and tube B, which was absorbing any excess water, went up by 2.45 grams. Okay, 8.4, the teacher repeated the experiment with a different sample of the oxide of copper. The teacher found that the oxide of copper produced 2.54 grams of copper and 0.72 grams of water, which is H2O. Two possible equations for the reaction are Cu2O plus H2O. Well, you can see there's two different equations there. And we've been given the relative atomic masses. H is 1, O is 16, copper is 63.5. We've been given the mass, we've been given the MR. Guess what we got to use? We've got to use the most important equation in chemistry, which is mass over MR times moles. You have to memorize that. You've also, if you look at this equation, it's basically showing that we've got equation 1 and 2. One is where there's a 2-to-1 ratio of copper to water. The second equation, there is a 1-to-1 ratio of copper to water. So basically, find the moles of copper, find the moles of water. Are they in a 2-to-1 ratio or a 1-to-1? And that's how you work out your answer. Which equation is correct? So let's get down to it. First of all, we want to work out what the moles of copper we have are. So we have 2.54 grams of copper. We divide it by its MR, which is 63.5. You can call it AR or MR. And that's going to give us our moles of copper. And the answer is, or should be, 0.04 moles of copper. Now, you might need to round here, but 0.04 moles of copper. Now we need to find out how many moles of water do we have. So we need to divide the mass of the water, which it told us in the equation, which I've circled here in the question, sorry, is 0.72 grams. We need to divide the 0.72 by the mR of water. Now, to work out the mR of water, you do 2 hydrogens plus an oxygen, which is 18, and you'll find you get 0.04 moles of water. So which equation above is right? The one where they're in a ratio of 2 to 1 or 1 to 1? We've got the identical amount of moles of copper, an identical amount of moles of water. And so what does that tell us? That tells us it's in a 1-to-1 ratio. The amount of copper to water is the same, 1-to-1. So which equation is correct? It's equation 2, because in equation 2, you have 1 lot of copper for every 1 lot of water. And there we go. How many marks did you get? All right, we're going to move on to the final question in this paper. So let's go. A student investigated the temperature change in the reaction between dilute sulfuric acid and potassium hydroxide solution. This is the method used. 1. Measure 25 centimeter cubed of potassium hydroxide solution into a polystyrene cup. Record the temperature of the solution. Add 2 centimeters of dilute sulfuric acid. Stir the solution. Record the temperature of the solution again. Repeat the steps 3 to 5 until a total of 20 centimeter cubed of dilute sulfuric acid has been added. Suggest why the student used a polystyrene cup instead of a glass beaker for the reaction. Well, we're recording the temperature. So what is it about a polystyrene cup and temperature? A polystyrene cup will reduce heat loss to the surroundings and give us a more accurate recording of our temperature change, okay, because it reduces heat loss. Why is it? Polystyrene is a better insulator than glass. Boom. Okay, for this next question, it says complete figure 11, plot the data from table 6, draw a line of best fit through these points, extend the lines of best fit until they cross, determine the volume of dilute sulfuric acid needed to completely react with 25 centimeter cubed of potassium hydroxide solution. Well, I need to get both the graph and the table on the page at the same time, and then let's go through and plot this up. So now this is just a case of whacking your points on. So you go to 0.0, 18.9, you find where it goes onto that graph, you smash the points on. So we've got 1, 2, 3, 4, 5, 6 points, crosses to put on. They're going to give you about half a mini square either side of the dot. So if you make a little error, like your one tiny square out, you'll probably get the mark. Okay, so on the y-axis, each square is equal to 0.2. How did I work that out? Well, you divide the value of the 10 squares by 10. So 2 by 10 gave me 0.2. On the x-axis, the value of the 10 little squares is 5. So you do 5 divided by 10 is 0.5 as we go across. So it's a little bit of a tricky numbers here, but that's because your chemistry separate GCSE. And it's right at the end of the paper. So they're testing you on this. So it's not the plotting that's hard, it's the working out how much each little square is worth when you go horizontal or vertical. Anyway, once you've got all your points plotted on, you're then going to draw a line of best fit. And then the question says it wants you to extend the line of best fit to when they cross, and then we can make a prediction based on where they cross later on. So what we want to do is draw a line of best fit through all of these points. Now you can see the line they've already done is a curved line. So the line we're going to do here is also curved. Now the next part of the question is to predict the volume of sulfuric acid needed to completely neutralize 25 centimeter cubed of potassium hydroxide. And it's the point where these two lines cross. And so it's 11 centimeter cubed. I'm circling it there. So you look along your x-axis, it's 11 centimeter cubed. And the next part to the question is, at what temperature has the reaction finished? Well, that's the point where the acid's been completely or has completely neutralized the KOH. And the temperature is going to be 27.5 degrees, roughly. Again, now looking at the y-axis for that. And so over here on the left, we can just write the volume of dilute sulfuric acid needed was 11 centimeter cubed. Actually, I've just noticed it said determine the overall temperature change, not the final temperature. So what was the overall temperature change? Well, we started at 18.9 and we finished at 27.5. So it's 27.5, take away 18.9. The overall temperature change is actually 8.6 degrees. So it wasn't asking for the final temperature, but determine the overall temperature change. Look where my red line started. It was about 18.9. And where it finished, where it crossed the other line, was 27.5. So we needed the difference between those two numbers. And finally, we got a 5-mark mole 1 or 6-mark mole 1. So the student repeated the investigation. The student used the solution, different concentrations from the first investigation. The student found 15.5 centimeter cubed of 0.5 mole per decimeter dilute sulfuric acid completely reacted with 25 centimeter cubed of potassium hydroxide solution. Here's the equation for the reaction. Calculate the concentration of the potassium hydroxide solution in mole per dm and in G grams per dm. We've been given the relative atomic mass, and what you should do is go through, highlight all the numbers and write down what the values are. So 15.5, that's a volume. 0.5 mole per decimeter is a concentration. Again, we've been given 25, that's a volume. We've got a ratio. You always work out the ratio of the two chemicals they're talking about. And then it says calculate the concentration of potassium hydroxide in moles per decimeter. So first, we have been given 15.5 and 0.5. So that's my starting point, and that's my sulfuric acid. So I want to do N over C times V. And make sure you do 15.5 divided by 1,000, and that will give you your decimeter volume. And then you're going to times that by the concentration of 0.5, and that's going to give you your moles of dilute sulfuric acid. Okie dokie. So now we have our moles of dilute sulfuric acid, which is 7.75 times 10 to the minus 3, or 0.0077. We now check out the ratio is 2 to 1 in our equation, which means I'm going to have double the amount of potassium hydroxide. So I'm going to have 0.0155 moles of potassium hydroxide, because you times your moles of sulfuric acid by 2. It now asks me to calculate the concentration of the potassium hydroxide. Well, I know the moles, so I need to divide it by the volume, which is 0.0155 is the moles, divided by the volume, which is 0.025, 25 over 1,000. Remember, we're changing to decimeters. That gives me a concentration of 0.62 moles per decimeter. Now, all I need to do is change that into grams per decimeter. So far, we've scored 4 marks. I need to change this into grams per decimeter. Guess what? You've been given the RAM, so work out the MR of KOH, and the KOH MR is 56. Okay, 39 plus 16 plus 1. We're going to do 0.62. We're going to that's the moles. So we're going to use our mass over MR. So we're going to go 0.62 times 56. We have a mass of 34.775 grams per decimeter. And that's your lot.
You're still here? It's over.